Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 25 and we will be now looking in detail on the freeze out effect on dopant atom concentration in this lecture. So, the outline will be we will look into what is known as a charge ionization. We have also looked earlier into incomplete ionization because of temperature variation. We will go into details of that, and there is also a field assisted incomplete ionization. So, we will be studying that. Then we will understand what is a thermal ionization probability, then look at to freeze out an ionization of dopant atoms. We will also have a look at what is known as a dwell time and electric field dependent charge local ionization. So, primarily the motivation of this lecture, which is lecture number 25, is to give you an idea that if the devices which are kept at cryo at very ultra low temperatures, if they tend to behave in a manner that there are no charge carriers available for transportation, then how does it influence the overall characteristics of the device? Not only that, you also need to also look into the fact that because of these incomplete ionization which is happening for whatever reasons, thermal or electric field dependent, there are some dopant species which are left unionized within the device itself. How does it influence the overall electrical characteristics of the device? That is the motivation for this lecture to happen. So, let us look at charge ionization, right, which we had discussed in our earlier lectures as well. What is charge ionization? Let me give you a brief idea for those who are new to this area. So, if you have a nucleus here and you have orbitals which are rotating and you have orbits around which the electrons are rotating, that is a very conventional sort of picture which I am picturing. Actually, it is a cloud of electrons and they are basically moving they are in the orbital spot. Now, let us suppose I give a thermal energy to this species, then this external electron here, which is the outermost shell electron, they will actually jump out and come to the free space, thereby converting this material, let us suppose phosphorus, into P plus, and there will be one electron which will be donated to the silicon. That is the basic idea of how a group 5 element is formed, that you end up having a fifth group element and you basically do ionization because the outermost electron can be easily moved to a free space. When I say free space, I basically mean into the conduction band, which means that it can participate in the flow of charge carriers. So, there will be a transport associated with this electron. That is what is defined as ionization, and this is basically a charge ionization which we are talking about. We define a factor here, and that is known as ionization fraction, and is given by ionized charge concentration at any point t and the maximum ionization concentration. So, typically if I say it is 100% ionized, it effectively means the ionization fraction is equals to 1, right. 100% ionization, right, will refer to as this IF, ionization fraction or factor, to be equals to 1. If it is say 50% ionized, it effectively means that IF will be around 0.5, right. So, just by looking at IF, I know how much percentage of the dopant species has been actually ionized. Let us look at the left hand side graph, which tells me the variation of ionization fraction with respect to temperature, right. As you can always understand, the maximum value for this will be equals to 1, which means 100% ionized, which is at the point number 1 here. This is where you will have this to be equals to 1, corresponding to 100% ionized, and there will be another edge which is at 0 Kelvin, it will be around 0, and that basically means 0% ionized. These are the two extremes which you will have. Now, somewhere in the middle where the temperature varies, as you can see, as the temperature starts to go down, the ionization potential, which is region 2, is a point where you see the ionization fraction actually drastically comes down, and this happens somewhere between 170 to 180 down to about 40 to 50. This region number 2 is the point where you see the ionization charge fraction dipping down drastically, and as you can understand, the thermal energies are not enough to promote the external electron to shift to a free charge space, and that is the reason the ionized charge fraction actually starts to drop down. However, you might note also from this graph that when you take T equals to 300 Kelvin, though we say that the ionization fraction is around 100%, in reality that might not be the case, right? There might be about 98 to 99% ionization taking place, because there might be some of the atoms which have not ionized and they are in their neutral state, and that does not account for the fraction, which means that if I dope with 100 dopant species, let us say 100 phosphorus atoms, if I get 100 electrons, then we define that to be as 100% ionized. So, this is the charge ionization principle which we follow, and we defined ionization fraction here. Now, let us look at incomplete ionization, and we have already done that. I will still go one step ahead and show it to you. If you remember the charge neutrality, PP basically means the number of holes which are generated in a p-type material is defined as PP. If you have charge neutrality condition, the number of free holes available must be equal to the number of acceptor ions which have actually accepted one extra electron and thereby turning that into a hole must be equal to each other. Or I can say that the number of electrons in an n-type material must be equals to number of donor species available. So, this and this are exactly the same. This is for a p-type semiconductor and this is for an n-type semiconductor, right. And for both the semiconductors we assume, and charge neutrality cannot be violated at any point of time, like charges, as you are all aware of, the net charge will still be equals to 0, right. And that happens only when the number of free electrons is exactly equals to the number of dopant species which have ionized with respect to each other. Now, if you multiply that Na with E of A, this F of EA is basically the ionization factor, right. This ionization probability of dopants. Obviously, as you can understand, if this is 1, then all the dopant species are ionized, and if it is less than 1, then depending upon the value of F of EA, we will have the value of N of A. So, there are two issues which get affected. The first effect is by temperature, and that is what we have already discussed till now, and that is referred to as a thermal ionization. If you look at this graph here, this is the thermal ionization. And then there is also ionization probability also gets affected by what is known as a field assisted ionization. I will try to explain to both of them. Thermal I have already explained to you in a detailed manner. Let me explain to you what is known as a field assisted ionization. Field assisted ionization basically means that, let us suppose the electron from the external dopant species gets promoted to a free space. However, within a very short period of time it gets recombined as well, because there are no external fields available, then it comes back to its original state of a neutral atom. However, in presence of a very large amount of electric field, there might be a case that the electron might actually drift away from the holes, because it is negatively charged and this is positively charged. Then we define that to be as a field assisted ionization. Another ionization is that the farthest electron, which is very far away from the nucleus of the atom, might come under the influence of an external electric field, and the external electric field will have so much amount of force on the electron that the electron can actually jump away from the influence of the nucleus, resulting in a free charge carrier, right. That is also referred to as a field assisted ionization. So, there are two types of ionizations which is prevalent. There are other ionizations as well, but for the particular lecture, two ionizations. One is a thermal ionization, another is a field assisted ionization, and these two ionizations play an important role as far as dopant species are concerned. If you look at the right hand side picture here, the schematic of a MOS device, a bulk MOSFET, psi s is basically the surface potential, which is basically the potential visible at silicon dioxide interface in the channel region, right. This is my source maybe, and this is the drain, and this voltage is drain to source voltage, which we see. Source is generally grounded. I have a source to bulk here and I have a gate to bulk here. Now, we define this to be as y, the transverse direction as y, and the longitudinal direction as x, right. Now, if you see, there are two regions of operation. One is just in the active region, right, and another is in the substrate region, in the well below the depletion, the region where you have a p-type silicon available. So, this is basically an inversion. So, I am using enhancement mode MOSFET if you see this dotted line here, this dotted line, though not very factually correct, but for understanding purpose this is perfectly fine. Below this dotted line you have the substrate region, above this dotted line you do have the substrate region, but that has been depleted, inverted, whatever. So, this is the pure depletion. There are therefore two elements which is available. One is Na of F, which is this one which I am talking about, right, which is again thermal and field assisted, and Na of F theta, where F theta is basically this expression which you see, and it also depends therefore on the VSB value. I will explain to you how this comes out in a sense. So there are two regions of operation where you actually have an ionization taking place, right. It can be complete, it can be incomplete. We will not go into details of that at this stage, but we will at least know the two operations here. The first one, which is Na of F, the first one which is here, is primarily because of the strong electric field present in the inversion region, or in very near to the when you apply a drain to source voltage, strong inversion is formed. When you apply a very large gate voltage, more than the threshold voltage, there is a strong amount of transverse layer electric field, because of which there are all the dopant species tend to give to you. So, this is not thermal, this is field assisted. If you look at charge neutrality, right, now under charge neutrality, I am assuming that perfect charge neutrality is maintained, then the overall electric field will be equals to 0, and therefore F of EA in that case equals to the thermal ionization probability. In absence of any electric field, whatever ionization is happening is primarily because of the thermal ionization. In this case, F theta is referred to as 1 over 1 plus alpha times exponential phi f plus VSB, phi f star plus VSB. VSB is the source to bulk. So, if you look at F theta value, let me write down for your much better understanding, it is 1 over 1 plus exponential, we have an alpha term here, phi f star, which is the Fermi potential which we discussed here in the previous turn, we have VSB, right. This is it, which tells me that if the VSB value increases, source to bulk increases, F theta value starts to reduce, right. And what does it tell me therefore? That when VSB actually becomes larger and larger, let us suppose, so my source is generally, this is the source, then the source is generally grounded, I apply a bias on the bulk side and I start go on increasing the potential, right, then the source to bulk potential starts to become larger and larger. And when it becomes, when it starts to become larger and larger, it tends to make my F theta smaller, which effectively means that the number of ionization particle is relatively smaller in this case, right. So, I will leave as an exercise to you to find out what is the physical reason behind it, but that is the notional picture which we get, right. Two things therefore take away from this slide. There are two types of ionization, one is in the substrate, pure substrate, one is near the depletion region. In case of there is no field assisted, it will be purely thermal in nature, right, and VSB and F theta are inversely proportional to each other, and therefore, as the value of VSB increases, you will have a lower and lower value of F theta, primarily meaning your ionization will be reduced in that case. Now, let us come to what is known as the freezing effect in devices. Let us assume that the way we speak about it is that if my F theta is around 20%, which means that my ionization is 0.2, right, 20%, which means for every 100 dopant or acceptor species which you are inserting into the system, only 20% or 20 number of species are contributing to the overall electron or hole concentration. We define that the silicon body has entered into a freeze out, right. So, just one thing I want to refer to before we move forward, this is referred to as the body or also referred to as a substrate. So, this is a body or a substrate which you see in this case. Now, in this case, as you can see, F theta is approximately equals to 20%, right. When it becomes F theta is equal to 20%, it freezes out. Now, the value of the impact ionization factor depends upon many other external sources, right. As I discussed with you, there will be thermal assisted, there will be field assisted ionization, right. Apart from that, though not perfectly proven as such, but it also gets influenced by the traps which are available in the body or in near the interface trap charges near the system. Why? Because traps are the domain, in energy domain they are low energy domain. So, any electron which comes out of it can easily sit on that domain, and therefore an electron which is coming out from donor species will be easily attracted by a trap. So, there are certain trap assisted ionization also happens. I will not go into details of that. So, there are multiple reasons why ionization happens, but when we study of only cryogenics, I am concentrating only on the temperature, everything else remains the same. So, the traps, their position with respect to silicon dioxide as well as with respect to body is almost fixed. So, the behavior which happens at 300 Kelvin almost same happens at 4.2 or 10 Kelvin, but thermal assisted traps are typically different from both the cases. Now, at 4.2 Kelvin or near 0 Kelvin, because of incomplete ionization, the effective Fermi level referred to as EF star, it becomes shifts to AF star instead of EF. So, let me show you what I was talking about. The same graph I had shown you in the previous lecture also, but if you look at this graph here, on the left hand side, this side is metal, right, this is your oxide and this is your semiconductor. So, I have an energy level of the vacuum which is constant across metal, oxide as well as a semiconductor for reasons well known to you. I have the conduction band on the metal side, I have the intrinsic Fermi level, I have the acceptor level shown in the brown, this is the acceptor level, right. So, it is a p-type semiconductor. I have a valence band here, so that is the valence band and this is my conduction band. Q chi of t is basically the electron affinity associated with it. Eg by 2 is basically the half of the band gap which we say. Now, let us concentrate only in these levels only. So, I have an acceptor ion, so it is basically a p type very close to the valence band, and therefore, the holes from the valence band can be moved towards the acceptor ion concentration. Now, interestingly, if there would have been complete ionization, 100% ionization, it effectively means all the acceptor species had accepted all the ions, then this is my Fermi level EF, which is very close to the valence band, almost indistinguishable from the valence band, right. However, because of incomplete ionization, the probability has lowered down and therefore, my EF star has gone slightly above EV. So, you see, as the value of the Fermi level becomes closer to the valence band, more is the concentration of holes available to me on the valence band, right. You have more number of p-type carriers available. So, when you had 100%, EF was very close to EV. Now, if you have incomplete ionization, that level has actually shifted to the top, showing that the probability has now lowered of finding holes at the valence band, and that is the reason your EF star in energy scale is slightly greater than EF, as you can see here, it is slightly greater than EF, correct, and that is justified also. So, please understand, we have not given any bias and therefore, you see the bands are not bent, they are perfectly flat, we have not given any bias. Still, because of incomplete ionization, because of freezing effect, the EF star is becoming larger and it is in energy domain, it is larger than that. The difference between EF star and EF is referred to as Q times del phi F, the change in the Fermi level. So, Q into del phi F gives you the change in the Fermi level, right, and that change happens because of incomplete. Why we are studying this? We are studying this because, as we had discussed earlier, at low temperature, incomplete thermal ionization will result in this shift in the Fermi level. Okay. Let us come to the thermal ionization probability. As I have already told you, f of theta is 1 over 1 plus alpha times exponential VSB plus phi f star. Phi f star is because of incomplete ionization, the fresh value of the Fermi level. So, if you take alpha equals to 0, then effectively what will happen? Let us take alpha equals to 0, the red colored curve here, this one. So, at alpha equals to 0, my f of theta becomes equals to 1, and that is the reason you see that it is perfectly straight line, right, which means I will always get 100% ionization. Do not worry what alpha is, an empirical constant at this time you will assume it to be. Now, let us see what happens if the alpha is a lower value or a lower value basically, and we are varying f theta with respect to VSB, source to bulk voltage. As you can see, at very low values of source to bulk voltage, f of theta is relatively large, right, and that is expected also, because f of theta is very small, sorry. So, at low values of VSB, right, this falls down, right, and your f of theta is relatively small in that case, right, and the reason it is like that is that as the VSB starts to go down, this is in the denominator, right. So, in the denominator, when you have, so this is for varying values of Na. So this was 10 to the power, so this is 10 to the power 9, right, and this is 10 to the power 18. So let us take up any one slide here, maybe we fix the value of VSB, and as you can see, as the Na, first of all, as the Na value goes on increasing, the F theta value goes on decreasing. Quite interesting. For a fixed value of VSB, as the value of Na, the accepted ion concentration goes on increasing from 10 to the power 9 to 10 to the power 18, for a fixed value of VSB, the F theta decreases, which means that the thermal ionization probability goes lower and lower for a higher and higher value of Na, right, and that is expected also. Why? Because if you have higher value of Na, the probability of incomplete ionization also becomes smaller and smaller, because most of the species will be able to contribute to the holes, and that is the reason you see it falls down. If you typically look at this particular point 10 to the power 9, I have got F theta as about 90%, whereas for low values it is somewhere around 10 to 15, about around 10% value which you get, right. This is one observation which you get. Therefore, if you want a full complete ionization to happen, so that contribution is 100%, two ways of doing it. One is reduce the value of Na, which we are anyway doing because of scaling, that makes you large, and keep your VSB to relatively to a smaller value. Then that will ensure to us that the thermal ionization probability is larger in that case. A more important point is, as you move ahead and make your VSB as large as possible, the F theta value also starts to increase, right. Okay. Let me now come to field assisted incomplete ionization. We were talking about thermal assisted. Now we field assisted ionization probability. One of the example which is there is known as a Poole-Frenkel effect, right. We might not be doing it in the class at this stage, but you might look into this Poole-Frenkel effect, which is incomplete ionization, field assisted based design. Now, as I told you, a second effect of incomplete dopant ionization is basically the field affected, and the ionization occurs due to the applied field. Applied field, which applied field? For example, look at the right hand side energy band diagram. I have applied, let us say, a voltage, right, on the metal side, a positive voltage, which effectively means that it has shifted down, and therefore with respect to that, my p type silicon has shifted up, right. So it has gone up, you see, there is a bending of the band taking place here, and that is because of the bias given on the metal side, right. Because it is a electron band diagram which we are referring to. So when we apply a positive bias on the metal side will go down because it is minus q times V, and therefore the semiconductor side with respect to metal will go up, and that is the reason you see that it is getting bent down towards the interface at the oxide layer. This is my oxide layer here, right. This is the metal layer and this is the semiconductor. Now let us go step by step and see what happens in this case, in the right hand side case. Now if you remember, there are even in a p-type semiconductor there is a accumulation, depletion, inversion, strong inversion, right. We all know these from your basic MOS device physics, you must be knowing. In strong inversion, the number of free electrons at the silicon dioxide interface is basically as much amount as there were number of holes initially there. Now let me take it to 4.2 Kelvin. The temperature has been kept to 4.2 Kelvin. I have a p-type semiconductor. Now if I apply gate voltage, right, then what happens is, this is the gate voltage V, gate to bulk, let us suppose, which has shifted my electron Fermi level or even the conduction band edge right to this particular point QFB, and there is a metal work function which is Q phi m, which is coming, and this is what you get. Now and that is going, and if you look at the semiconductor side, then this is my valence band here, this is my effective Fermi potential because of incomplete ionization referred to as EF star, this is my conduction band, this is my vacuum level, right. Now if we just turn our attention to the number of holes in this case, then we will see that EF star, if I assume EF star, this is EA is this, I should say this one is the EA, right, and it is falling. Obviously the accepted ion concentration will also fall if you apply a bias. Assuming that the Fermi level is constant, held constant, then you see near the surface the difference between the Fermi level and the valence band is relatively large as compared to the bulk. So this is the bulk side which you are moving, and this is the surface here, right. So which means that before the strong inversion has set in, this is not a strong inversion case by the way, before a strong inversion sets in, the Fermi level, the difference between the Fermi level, which is EF here and EV at the bottom, is so large that the probability of finding electrons are very, very low, which means it is depleted. So, the interface has been depleted, whereas bulk has got still large number of holes available to us, right. Now, if you do an n type, the bending will be in the reverse direction, right. If you do an n type, the bending will be in the reverse direction. It will be something like this, right. I will not go into details of that. I have kept into p type and silicon I am using. So, it is basically I am trying to invert the channel, so making it n type. So, the bulk is basically p type in this case, right. Del QF star is basically the difference between the intrinsic level and the modified Fermi level because of the incomplete ionization, right, and that is what you get here in this case, right. Now, you see the Fermi level is not changing because if you remember a basic fundamental principle that there can be only flow of charge carriers when there is when the Fermi level varies with respect to x, if x is this direction, right. So, which means that if there is a dEf dx, then only there is a current flow. However, since there is no current flow at this stage, because we are not applying any drain to source bias, we are only applying a gate bias, there is Fermi level is almost constant in that case. So, that is the reason why we define this to be as an incomplete ionization. Let me now come to the last stage before we end the session here. So, let me compare now p type silicon only at 4.2 Kelvin again here, 4.2 Kelvin here, but let us look at the field assisted ionization difference. On the left hand side, since I did not apply any bias, there is no field assisted ionization, and as you can see EF, EA, EV, everything is perfectly straight line, right. But if you look at the left hand side where it is a field assisted, then this shows the ionization condition of the dopant, whereas this is the freeze out condition on the left. So, the left gives you a freeze out condition without electric field based ionization, and the right hand side gives you just a comparison between the two, and as you can see here, the effective Fermi level EF star is actually much larger as compared to this. Now, if you look at this interface also, this QF star is basically at the interface at silicon dioxide interface is referred to as the difference between EF star and EI. EI is the intrinsic Fermi level. So, the difference between the two gives the effective change in the Fermi potential because of incomplete ionization. So, with this, let me stop and recapitulate what we did in this lecture 25. We understood what is freeze out, ionization of dopant, how the effective Fermi level changes with respect to thermal as well as with respect to electric field assisted ionization, and we also had two formulas where dependency of the ionization probability with respect to VSB was shown to you. VSB is the source to bulk voltage is shown to you, and these will be important when we do the cryogenic electronics in a larger sense. So, with this, let me stop at this stage. Hope you enjoyed the lecture. We will meet in the next lecture again. Thank you.